All right, so alcohol, chapter 17, making ethanol as a biofuel. This is something that we touched back in IGCSE as a small part of the topic, a possibility, a probability for which some countries on the planet are already doing it, while some do not exactly have the need for it, so they are not going with it yet. So ethanol C2H5OH is the most widely used alcohol of the entire homologous series of alcohols, and usually the crops like sugarcane and sugar beet are fermented, though many of the fruits are also converted into alcohol, grapes being one on the top of the list. But yeah, most of the time in most of the countries, since sugarcane and sugar beet come as cheap crops, so we ferment them to convert them into ethanol. Now, ethanol is a biofuel and it burns with a clean flame. It has very less uh, chances to be converted into carbon monoxide or other toxic gases. So the release of carbon dioxide, or what we usually call as a carbon dioxide signature, is usually less as compared to other fuels, specifically if we compare it with petrol. So we call it a biofuel because we can actually mix it with petrol, and since it's soluble with petrol, so we can use it with good percentages. 40-60, 50-50, 70-30 are the correct percentages in which the word is using it, along with petrol or diesel. One of the top countries in the world to do that is Brazil. So the production was very simple, and we also studied one more reaction. And back in chapter number 15, where we were talking about ethene from the cracking of fractions from crude oil, we studied that we can go with some addition reaction and we can add water to steam. This was basically the hydration of ethene, and we specifically called it electrophilic addition back there. So this electrophilic addition was the addition to double bond, and this HOH was converting this specific ethene molecule alkene into alcohols. This was done in the presence of H3PO4 phosphoric 5 acid as a catalyst, and this is the same reaction that we studied back in IGCSE. Though in IGCSE, we only study the reaction and its condition, but in AS, we specifically discuss it as an electrophilic addition reaction, where we also discuss the Markovnikov rule and discuss what is going to happen in this reaction in case of symmetric and asymmetrical alkenes. Now, this was all revision. Moving forward, this is relatively cheap, continuous process, especially for countries with their own reserves of crude oil. Ethanol made this way still costs more than petrol, as well as using up our remaining oil reserves. So Brazil is one of the countries that started making ethanol on a larger scale. However, they do not use ethene. They start with sugar extracted from sugarcane. The sugar solution is fermented in batches with yeast to produce ethanol as a fuel for our cars. Now, fermentation only needs a warm temperature to take place. We know that around 37 degrees centigrade, we know around 37 degrees centigrade, this process goes on best. With a little less temperature, uh, the yeast stops or slows down on making this ethanol. A little higher temperature, the yeast is totally denatured. So we can't go for a lower or a high temperature, but a balanced temperature and a balanced pH can actually be great for the production of alcohol. Now, ethanol made needs to be distilled from the reaction mixture. This requires energy, but more sugarcane or sugar beet in colder climates can be grown each year. So, ethanol made this way is more like a renewable fuel. Unlike fossil fuels still remain as uh, a non-renewable fuel. So, this has a great advantage on top of it. So ethanol itself can be used in cars with adapted engines or normal cars with as a mixture with petrol. This is currently being done in many countries around the world, not just Brazil. Well, we can also go with this one. But the environment could really benefit if we start using more ethanol as fuel. A huge volume of carbon dioxide given up from fossil fuels is causing global climate change, but the carbon dioxide is also given up during the fermentation of sugar as well as when the ethanol burns. So this is still a question. Well, I actually count this question as a big question mark. I take it as a red flag because we uh, go with this kind of calculation for our own mental ease, well, I don't think I don't see a big change for it. Well, there are both kinds of groups. You can always vouch for the other group if you want to, but I still have this question not figured out, that why we're going to produce a crop and not feed it to the hungry, instead to feed it to the cars for a luxury, because cars are still a luxury when it comes to choose between hunger and car. Of course, that is pretty much understandable. Well, let's not go into further detail for that discussion. However, carbon dioxide released into the atmosphere is offset by carbon dioxide absorbed by the photosynthesis. This is what we usually discuss. This is the most important point that they come up with. And that's how they say that it has a less carbon dioxide footprint than in comparison to petrol, which does not have that kind of carbon dioxide footprint. Well, discussion for some other day. Let's get to the actual topic. So the homologous series of alcohols. Alcohols are organic molecules. They have the hydroxyl group, OH group attached to it, which converts them into alcohol. So we call this the main functional group. With one hydroxyl group substituted into an alkane molecule, this becomes the formula. Now, we actually call these alkenols. And to be honest, the alcohols in O levels and A levels is mostly alkenols. We do not tend to go with other kind of alcohols for the discussion. I mean, we never talk about alkenes, an OH group added to alkenes, or an OH group added to alkynes, or an OH group added to other benzene-based systems, though we're going to discuss the benzene-based systems and the alcoholic group, the main phenol group, as a part of A2, but that's about it. So if I call them alkenols, and if I say that we study the alkenols, that's why we have this stem as the name, as the ending part of the name. We can also call it a suffix. So anol is the suffix that we commonly use. So we stick with it. Well, if I talk about alkenols, when I say alkenols, I am trying to pronounce it in a way that you understand we're talking about the word enol. Now, since enol represents the single bond and the ol part, both of them, enols actually represent the double bond and the OH part or the ol part along with it. Well, there are many past paper questions which talk about alkenols. So I hope this all makes sense to you and you understand the difference between alkenols and alkenols. And if there is some other related name comes as a part of past papers or as a part of your question in exams, you're mentally prepared for it since you understand what the different stems or suffixes mean at this point. Moving on, classifying alcohols, we can easily classify them into primary, secondary, and tertiary. The rule stays the same. So the carbon which is connected to the OH group, if that carbon is connected to just one carbon directly, it's primary. If that carbon connected two other carbons directly, in this case, then that's secondary. And if that carbon is attached to three other carbon atoms directly, that is a tertiary alcohol. Now, the naming is done in the same way as we practiced before. So I think this should be easier for you. However, there is a small change over here. You see that the numbering comes before the O part, since OH can be attached on anywhere in the chain, since it doesn't exactly have to be a terminal carbon. So that's why the numbering comes before the O part. I hope this clarifies it. Also, this kind of name gives you the idea that if we have two numbers to represent in a chain, one goes for the alcohol and one goes for our branch, wherever that branch is. So that's how it's named. So I think this also clarifies the nomenclature part for alcohols, no matter it's primary or it's secondary or it's tertiary alcohol. I hope you get the point, right? Do you?
Yes.
Great. So moving on, propanol is classified as a primary alcohol. The carbon atom bonded to the OH group is attached to one other carbon atom. We have already studied it. It's easy. So propan-2-ol is secondary because of two other carbon atoms attached. And 2-methyl propan-2-ol is the example of tertiary because attached to three other. And remember, as soon as we go for some kind of reaction and this OH group is detached from this carbon, remember that this one is going to form a carbocation, which is going to be the most stable one in this case. Don't forget these facts, because if you understand the carbocation fact, you're already mentally prepared for a reaction in which the CO bond breaks. if the CO bond breaks? Well, the OH bond also can break, so we are going to study different reactions in which different things can happen. Either the OH bond breaks or the CO bond breaks, right? So there are also alcohols with more than one OH group. We came across examples in 15.4. For example, alkene is oxidized to form a diol. That was ethane 1,2-diol. And I hope this gives you the idea how to name these. Now, this gives you the idea that if all groups are more, then you need to go with prefixes separately for the all groups, in which a single ol means a single OH group. If there are two OH groups, then we write go for diol. If there are three OH groups, we go for triol. If there are four OH groups, we go for tetraol. And after tetra, the naming tends to be the same as per the naming of the conventional carbon chains that we commonly use, penta, hexa, hepta, octa. So I understand, I hope you understand too, that how do we name for substances that have multiple OH groups more than one, not just talking about the twos, but there are examples of triols and tetrols in past papers. So I hope you understand how do we name them. Now remember, when you put a die over here, there are supposed to be two numbers over here. It can be 1, 2, it can be any other numbers. They're not by push 1, 2. They can be changed as per the chain length or wherever the OH groups are attached, but there are supposed to be two numbers. Remember, two numbers, and die represent those two numbers. If there's tri, there are supposed to be three different digits over here, or they can be the same digits too, or that is possible. 113, 123, 112. These are possibilities for trials. So that is also possible. So keep that in mind that along with these prefixes that we use for the whole parts, the numbers also represent the same thing. So these are some clear rules of nomenclature which always help us figure out the right name in case of a question like that in paper 1 or 2. So this is the structural formula, and we specifically put it this way to give the reader the idea that one OH belongs to one carbon atom and the other OH belongs to the other carbon atom. That's actually a good way of writing it, because if we write it like this, it's better understood by the reader. So instead of doing something like this, which completely does not make sense, right? So we tend not to do it this way. It's better. However, there are some MCQs where it may be written like this. That's somewhat acceptable, but remember, the one written in the book is preferable because that's the standard way of naming it. Okay, so hydroxy groups. Now, alcohol groups, OH groups, which we previously called hydroxyl groups, we may also call them hydroxy as well. Now, hydroxy is a term that we commonly use for them when there are other functional groups also attached to the structures. That is also a possibility. Well, without the other functional groups attached to it, we may also use the hydroxy word. That's fine. This word can represent the OH group. Okay, so are bonded to CH2 group, but both are classified as primary. On the other hand, a diol such as propane 1,2-diol has one primary and one secondary OH group with its in molecule. Now, this means that we are talking about CH2, now CH, OH, CH3, and I may write this OH over here, I may write it below, under, it doesn't really matter. We, when we look at this structure, we understand there is one primary and there is one secondary. Now, when you look at this structure, you should be able to understand which one's primary. This one's primary, and I should really do it with a different color. This one's primary because the chain length is singular in terms of this perception. But if I talk about this one, actually, this one is secondary because the chain length has two carbon atoms in perception of this carbon. So we need to understand which one's primary and which one's secondary at this point. Okay, so that is one more way how the examiners can give you a confusing question. So keep this in mind because the reactions do tend to differ for primary and secondary sometimes. So if you have the idea of primary part or secondary part, or if a molecule contains both, one of each, that is also a possibility. So they have discussed the possibility over here. Okay, so moving on, properties of alcohol. Now, alcohols have higher boiling points than expected when compared with other organic molecules with simple relative molecular masses. Now, this is a very important point that they are discussing. Now, we can actually directly relate this point back to the bonding chapter, and they're going to discuss the exact same thing in the upcoming sentences, how even methanol and alcohol with the lowest molar mass is a liquid at room temperature. Now, this has only one carbon in its chain. Now, usually with one carbon in the chain or with two carbon in the chain, for example, if I talk about CH4 or I talk about C2H6, if I talk about C2H4 or if I talk about C2H2, now I'm putting different examples because this one is an alkane, this one is an alkene, this one is an alkyne, and at the same time, C2H6. So my bad, it shouldn't be H6, C2H5OH. This one also has two carbons. This is ethanol. Now, out of all of them, only ethanol is a liquid at room temperature. The rest are gases. Now, they are gases because their molecular masses are so small. But apart from that, there is one big reason at it. And that big reason is hydrogen bonding between alcohol molecules. Now, he has clearly defined the section which describes it, but apart from that, take a look at these. These have simple molecular forces, all right? We're talking about ID forces. Now, these ID forces are going to be very insignificant. Why? Because the size or the mass of the molecule is very small, and the points, contact points, are very less. Now, in that case, that what we have discussed back in chapter number 4 for bonding and lesson number or insignificant ID forces, they tend to be gases at room temperature. Well, apart from ID forces, contact point for molar mass as a factors can discuss, it does have hydrogen bond. How? Let's understand it. C2H5OH. Now, this carbon has two lone pairs, because of which it can really easily make a hydrogen bond with another hydrogen of specifically this hydrogen of another molecule. Okay, because of these hydrogen bonding, this has some stronger forces of attraction between molecules, which results in them being liquid at room temperature. Even methanol is a liquid, and methanol has only one carbon atom in its chain. As it's actually not a chain, it's a single atom. So uh, this also explains why the smaller alcohol molecules are so miscible, mix and dissolve well in water, which means, as we have studied, and this we have studied back in IGCSE as well as in AS, that all small alcohols are very much miscible in water in all proportions. For example, water and ethanol mix in all proportions, no matter 10% of water or 90% of alcohol, or the vice versa, or 80-20, or 60-40, or 70-30, whatever combination you're going to come up with, water and ethanol are always going to dissolve completely. And that's why we have this term miscible liquid-liquid mixing. So it gives you the idea, and that's because of hydrogen bonding. Now, water can also have hydrogen bonds, and these hydrogen bonds are because of the lone pairs present on oxygen, the big electronegative difference between oxygen and oxygen and hydrogen both present as a part of the alcohol molecule, as well as water. So the hydrogen bonds actually make them mix well. Now, these reasons have been discussed in those chapters as well. Now, when you're practicing paper 4 questions and then questions related to organic may seem difficult, But now, since you're done with this part, you are done with alcohols and their properties and how they're soluble in water, or why they are mostly liquids at room temperature, and why hydrogen bonding is important as a part of stronger forces apart from IDID forces in them. So this would give you the idea how to solve those questions correctly, right? So this also brings us to one more important point, comparing the acidity of alcohols and water. Now, when I use the word acidity, remember, we use this word wherever the hydrogen can be released separately as H positive ion. Now remember, the acid is an acid because or it can give away the hydrogen ion. Now, whenever I use the word acidity of alcohols, or maybe I call it for water, it is probably the capacity of an alcohol to give away the hydrogen as H positive ions, or the capacity of water to give away the hydrogen as hydrogen ions. So let's discuss that in detail. Once dissolved in water, ethanol molecules do not dissociate or split up to any great extent, although there is a very small degree of dissociation, and there is some ethanol which is converted into eth oxide ion. Now, that's how we name it. Before I move any further, remember, ethanol will be giving away hydrogen, and that hydrogen would be a part of hydroxyline, the hydroxy molecule portion of the molecule, but the remaining part is named as eth oxide. So if you're breaking down methanol, it would be methoxide. If you're breaking propanol, this would be propoxide. That's how we name it. There are different names used in past papers for different equations like this one. So you should be capable of naming the ions. Whenever we take out hydrogen ion, the H positive out of it, we have a proper negative ion left after it, and you should be capable of naming it. So the eth oxide ion. Now the position of equilibrium lies well over to the left, which means the forward reaction is gone a very little towards the right, so favoring the undissociated C2H5 C2H5OH molecules. Even compared to the dissociation of water molecules, the water can also dissociate, though that happens a very little. We have studied that back in the acid alkali chapter. The concentration of H positive ions is much lower, so we can say that alcohol is a weaker acid than water. Its molecules are less likely to dissociate and form H positive ions. When we say something is weaker acid, it means that it even produces less number of H positive ions than water. Now, we need to understand why ethanol is a weaker acid than water, which means water can easily break up and give H positive ions in comparison to ethanol. This is what this line means. Although both of them are giving very less number of H positive ions, but we can still, in comparison, can say ethanol is a weaker acid than water. Yeah, but why is that so? Let's discuss. Now, the molecules are less likely to dissociate and form H positive ions. This is because of the electron donating alkyl or ethyl group bonded to the negatively charged OH hydrogen oxygen atom of the ethoxide ion. Now, this needs to be explained. Let's explain it. There is an entire C2H5 connected to this H, which is connected to O, which is then connected to H. Now we do understand that this bonds break, oxygen tends to keep the entire bond. That's how it is converted into C2H5O negative. And this hydrogen is given out then in the form of H positive ion. Now we do understand that this happens less because of the presence of this. Why? This is an electron donating group. Alkyl groups are all electron donating group, no matter it's methyl or ethyl or propyl, whatever group is that, they're all electron donating groups. What electron donating groups tend to do is that they have a positive inductive effect. They try to support the other atoms. They try to stabilize the charge concentration. So what happens is that the positive inductive effect of the ethyl group has the effect of concentrating more negative charge on this oxygen atom. So the ethoxide ion more readily accepts hydrogen ion uh, than the hydroxide ion from the dissociation of water. the hydroxide ion only has a hydrogen atom bonded to it. And that's actually where we need to compare it with water. This is the structure of water. Now, we do understand that the oxygen is going to keep this bond and the hydrogen will be given out as H positive, and that's how this oxygen tends to be OH negative. But in this case, there is no positive inductive effect, right? So this positive inductive effect actually makes the oxygen easily accept an H positive ion, which makes this reaction go more to the reverse or the backside. As in this case, it goes a little less in comparison, which keeps it in more it in the molecular form, less H positive given out. This keeps it lesser in the molecular form, more H positive given out. So we can easily call this one a better acid and this one as a weaker acid, right? So that's the explanation to the structures where there might be an alkyl group or the absence of alkyl group. I hope you understand the difference, but if there are any questions and confusions, this is the right time to ask.
It's fine.
All right. Let's move forward then. The questions in the book over here might seem childish, but these questions are always the ones to begin with when you're going to start past paper practice. Go for the book questions first, and then the past paper questions become a little less difficult than what they already are. So 17.2 reactions to make alcohols. Now, the alcohols can be produced many ways, though we started off with a couple of methods of production of alcohols, and those methods were also part of IGCSE. So I hope you remember that one, we were producing alcohols from hydration of alkenes. Specifically, ethene was there to form ethanol. So you are already familiar with one type of reaction that can do it. Okay. So that's the first type you studied back in IGCSE, and you have the same as the first reaction over here. Now, moving on, don't forget that we have already studied fermentation as a way to make alcohol. So that's not listed in one of these top reactions, but this discusses in which chapter you have studied to form alcohol. Now, if you look at it, section 15.4 back in chapter of hydrocarbons, chapter 15 was the hydrocarbons chapter. We first studied alkanes, then we studied alkenes. In alkenes, there was an oxidation reaction, oxidation of alkenes, and this specific reaction actually gave us diols, not just simple alcohols. The alcohols which actually have two hydroxy groups, so diols were there. So this was actually happening because of the cold dilute acidified potassium manganate was reacting with an alkene to form these diols. Next up, in chapter number 16, we had a nucleophilic substitution reaction. Hydrolysis in this case, hydrolysis with an alkali or hydrolysis with water. Hydrolysis with water was slow, though it also formed alcohols. Hydrolysis with an alkali was faster with a little bit of different products. We weren't getting HBr, we were getting NABr out of it. So they were producing alcohols on a much better rate. So don't forget that nucleophilic substitution or hydrolysis with either in the presence of alkali or just water was both possible in the cases. Okay. So I discussed an extra case which was not written here, but was a part of the start of chapter 16. Okay. So moving on, there are some other ways to produce it too. Let's discuss all the ways. It's better that they are discussing some ways related to the previous chapters, some ways related to this chapter, and they also included a way that they're going to discuss in the next chapter, the last chapter of AS, chapter number 18. So that's a good thing that they actually included everything on here on a single page, which gives the student the key ideas of formation of alcohols from different chapters. So since it's in the middle of the starting and the ending chapters of the AS, it means that all the chapters that consist of formation of alcohols are listed over here, which is actually a good thing. So the reduction of an aldehyde group that we're gonna, a homologous series that we're going to study in the last chapter, in the next chapter. So to form primary alcohols, or we can use ketones, which actually form secondary alcohols with a strong reducing agent. This time we are using a reducing agent that we didn't study back in IGCSE, NABH4 or LiALH4. As you can see, a lot of hydrogen atoms in there, which when added to any of your molecule would reduce it. And in this case, the reduction product is actually alcohols. Now, in this case, when we are using an aldehyde, which we are doing in the first reaction, or when we are using a ketone, which we are using in the following or the second reaction, we're producing a primary alcohol. This one is a primary alcohol, and this one actually is a secondary alcohol, as also stated in the text. So not just that, a carboxylic acid can also be reduced back into alcohol. For example, ethanoic acid, the common carboxylic acid that we have used back in IGCSE can be reduced by using the same strong reducing agents, NABH4 or LiALH4, and they can be converted into ethanol. Now, these specific chapter 18 and chapter 17 reactions are written over here, but they haven't yet discussed the complete set of details or conditions for these reactions, which they're going to do later. When you're going to see the conditions for these reactions, you're going to see that along with the reducing agents, we tend not to use waters. We use them under dry conditions and non-aqueous conditions. So the conditions in both of these reactions are not properly mentioned over here. Like in the previous oxidizing agent, they mentioned whether it was cold or dilute or concentrated, whatever the case was. Since we only discussed the cold dilute reactions. So remember, they are going to discuss details on the upcoming pages, how we can keep them dry or non-aqueous, because water interferes with this reaction a little bit differently. Though there is another way of doing it, and that is with H2, with nickel and heat. This is hydrogenation reaction. Now, this has a small or over here, which means we can do the same reaction. Instead of NABH4 or LiALH4, we can use hydrogenation reaction in the presence of nickel as a catalyst and heat. Remember, hydrogenation was possible. We studied this specific reaction in chapter number 15, hydrocarbons, where we were able to convert alkenes back into alkanes with the help of hydrogenation. And that's how we were capable of converting actually the cooking oils or the vegetable oils into margarine. This was also given in chapter 15. Now they are talking about that we can convert carboxylic acid back into alcohols with the help of hydrogenation reaction. All right. There is a small or over here. You can discuss it as a separate bullet point. It's better to put it up as a separate bullet point because that is also possible, and that has been taken by past paper questions way too many times. Now, moving on, hydrolysis of an ester is also possible by heating with a dilute acid or alkali, something we studied back in IGCSE. With acid, what's going to happen? We're going to produce this carboxylic acid, and we're going to produce an alcohol, of course. Or even if when we try alkali, we produce the sodium salt of the carboxylic acid, but the alcohol tends to remain the same. This product is not changed. Okay, so if you're talking about alcohol, whether you use the acid or you use the alkali, this part of the product does not change. So we can safely say that in both the cases, you produce the alcohol. This is a hydrolysis reaction. Remember, the water tends to break down the entire molecule with the help of breaking down of water itself. Okay, so moving forward, I guess this was a big page of reactions, and yeah, we're going to study a lot more reactions towards the end of the book. So reaction of alcohols first comes combustion. Just like back in IGCSE, this was the very first reaction that we studied, and we knew that alcohol tends to go with complete combustion and a good supply of air with a clean blue flame, and it produces carbon dioxide and water. Now, this reaction was always a little tricky. Let me go through that old trick again that we discussed back in IGCSE, that how to balance the oxygen atoms. Now, in this case, many times the students tend to forget that there is a single oxygen atom present in the ethanol. And they tend to balance the oxygen based upon this number and this number over here directly with this oxygen, which always comes as a mistake. You can see there are 4 total oxygen atoms in carbon dioxide set, and there are a total of 3 in water, so there are a total of 7. So we only mentioned 3 over here. We never mentioned 3.5 to make it a complete 7. Why? Because there was 1 oxygen atom over here too. So whenever you're balancing these equations, the combustion equation of alcohols, whether they are complete equation, complete combustion equations, or incomplete ones, do not forget the fact that 1 oxygen, or maybe the balancing number changes the whole situation, there are oxygen atom or atoms present in the structure of alcohol itself, right? Now, substitution to form a halogen alkane. This seems like exactly the reverse of what we did back in the halogen alkanes chapter. We actually used NaOH and we converted halogen alkanes. For example, if this was the halogen alkane we discussed back in the last chapter, the previous one, chapter 16, we used this and we easily converted the whole thing into an alcohol and an NABR. Now, we can exactly go for the reverse and we can convert the alcohol back into a halogen alkane with, again, the nucleophilic substitution. Now, this nucleophilic substitution will be done with a hydrogen halide, such as hydrogen chloride. The OH group would be replaced by a halogen atom. This produces a halogen alkane for us. So this is the way that we can convert it back into a halogen alkane. This HCl can convert it to chlorethane. If you're going to use HBr, bromethane, in the similar way, we can convert it into any kind of halogen alkane that we like. So the example only talks about chloroalkane. The dry hydrogen chloride gas for the reaction can be made in situ. Now, this is the first time then that we are going to discuss this word in situ. It's pronounced in situ, and in situ means with whatever reactant that you need, that's made right in the reaction vessel with the help of 2 reactants. Now, this actually defines clearly the difference between the word reactant and the word reagent. Now, we have been using these 2 words again and again in an equation, and we have been talking about it, but really, this is the point where it is confirmed what's the difference between the 2. Now, you have already seen that the reaction itself is talking about this. We're talking about taking ethanol. We're talking about reacting it with HCl. We're talking about converting it into a halogen alkane, CH2Cl, and giving away some water. Now, this is the actual reaction. This is the first reactant. This is the second reactant. But if I talk about reagents, this is the first reagent, this is the second reagent, this is the third reagent. What does the word reagent mean? Reagent means the exact chemical we are going to throw into our reaction vessel. Now, we throw this ethanol, we throw this NaCl, and we throw this H2SO4 into the reaction vessel. That's a separate point that NaCl and H2SO4 react to produce this HCl, which is the actual reactant for this reaction. So HCl is a reactant for the reaction, but is not a reagent, which means we directly do not react it with HCl. We produce it in situ. That's the main difference between reactant and reagent, which clarifies it for the students. Now, since we have clarified it at this point, so you need to be very vigilant how the examiner is posing the questions. Now, examiners very cleverly choose their words in A levels because they understand the student is capable of understanding the difference between the two. So they put up their words to clarify what they're actually doing. I'm not saying that bluff, they never bluff. They actually go with the exact wording required. And if you clearly understand the difference between the two, you would exactly understand or take the meaning as the examiner wants you to. Am I clear with the reactant and reagent difference?
And can you just repeat it once more?
The reactant is ethanol, this one. Okay, I'm gonna use different colors. Ethanol is your first reactant, HCl is your second reactant. Now let's go with reagents. When I talk about reagents, ethanol is your first reagent, NaCl is your second, H2SO4 is your third reagent. What that means is the reaction vessel I'm about to explain to you, we are not going to put HCl in that uh, reaction mixture. We're only going to put ethanol. We're going to then put NaCl and H2SO4. That's another point, that NaCl and H2SO4 react to produce our reactant. So these are the reagents. Reagents, why? Because they go into the reaction vessel. HCl is the reactant. It's not the reagent. Why? We do not directly put HCl into the reaction mixture. Instead, we put NaCl and H2SO4. That's what the word reagent means. Reagent means the chemical that you throw into the reaction mixture. Reactant means the actual chemical that is because of which the whole reaction is taking place. Whether you put it in its original form into the reaction mixture or you produced it in situ in the reaction vessel. It does not matter.
All right.
Great. So if you're clear between the differences, let's move forward. So with this reaction being given, I hope you are going to understand the halogenation of an alcohol better. The alcohol is heated under reflux in this kind of structure with the reactants to make halogen alkane. The halogen alkane made can be distilled off from the reaction mixture, collected at oily droplets under water. Since this does not mix in water, so we can safely separate it. So bromethane being distilled off following reaction between ethanol and hydrogen bromide, and the white solid visible in the pear-shaped flask is sodium bromide crystal, which is right over here. Now, the sodium bromide reacts with the concentrated sulfuric or phosphoric acid to make hydrogen bromide needed for the reaction. So hydrogen bromide is the reactant in the reaction, but it's not the reagent, because we never put in any hydrogen bromide into the vessel. We only put sodium bromide and sulfuric acid. You may have used phosphoric acid, it's entirely up to you. So that's why the substitution reaction with hydrogen bromide, HBr, can be made by using potassium bromide or concentrated phosphoric or sulfuric acid. So that depends entirely up to you. For your questions in past papers, what we tend to say is that you can use any of the sodium halides. You can use NaX, which means NaCl, NaBr, any of those, or KX, which means potassium chloride or potassium bromide, and both the acid H2SO4 or H3PO4 can be used for the production of the hydrogen halide. Now, these are going to react and going to give you the HX that you require as a reactant for the reaction. All right?
Yes.
So the nucleophilic substitution by the halide takes place after the OH group has accepted an H positive ion from the acid. This makes the CO bond in the alcohol easier to break, and water is given off. Now, this clearly gives you the idea that we are breaking the CO bond. Okay, in the case of alcohols, as I have discussed previously, I'm going to put it clearly over here, H2, in fact, let's break it down. CH3, CH2, OH. Now, this is the structure for ethanol. There are some cases in which we are going to break this bond and attach something different to it. Like in this nucleophilic substitution reaction, we actually attach Cl to it to form the halogen alkane, which means the break of PO bond. There might be a reaction in which we only break this OH bond and the rest remains intact, like we did back in esterification reaction in IGCSE. Although I'm not repeating the esterification reaction in front of you right now, but I hope giving this example gives you an idea that we do not necessarily need to break the whole thing off. So we may break this OH bond or we may break this CO bond in case of alcohol. So whenever you see a reaction, clearly notice what you're breaking off from this reaction, and then you can actually answer the question. That is something that is usually discussed in paper one. Okay. So moving on, Sulfur dichloride oxide, or SOCl2, something that I specifically named as cyanide chloride, and I asked you to write it in the book in the previous chapters because we're going to use this again and again afterwards in organic chemistry that is important, can also be used to substitute a chlorine atom into an alcohol molecule and to convert the alcohol into halogen alkanes. So there you go. When you react an alcohol with cyanide chloride, it would give you a halogen alkane. Now, this also breaks the CO bond, the entire CO bond, and the entire OH molecule part is given out, and then the C2H5 is connected to a halogen. Notice that in this reaction, the two byproducts, HCl and SO2, are both gases. These gases escape from the reaction mixture. The halogen alkane is formed without the need to heat the reaction mixture. All right. So this is somewhat an easier way of forming it. Okay. So you are also going to see this kind of reaction for quantitative chemistry questions. You might have already noticed the common quantitative chemistry questions in which there is formation of two gases and they discuss both the gases for number of moles calculation, which makes it a little bit tricky. But if you understand that both of them are gases and both of them are going to leave the system in the form of gases, it's easier to point out that for every mole of alcohol and cyanide chloride in this reaction, you're producing 2 moles of gases, 1 mole for HCl and 1 mole for SO2. So if any questions with the same equation, but related to the moles chapter, you shouldn't get confused. Cambridge actually tries to use any equation from your book for any other purposes, be it for a bonding chapter, be it correlated to a quantitative chemistry chapter, be it correlated to the properties that we have studied in inorganic chemistry. So they can pick out any part of the book and correlate with any other, assuming that the student is himself or herself capable to do so. That's why I keep on connecting the dots of different parts of the book to the chapter we're currently at. Okay, moving on. Phosphorus halides. Now, phosphorus halides, whether PCl5 or PCl3 or PBr5 or PBr3, they have the necessary halogen atoms to provide for the substitution reactions. And alcohols, either reacting with PCl5 or reacting with PCl3, do tend to be converted into halogen alkanes. But the conditions are slightly different for both the reactions. So let's go through it. With PCl5, we use solid phosphorus 5 chloride. The release of acidic hydrogen chloride fumes from this reaction are actually a test for the hydroxyl group. You are only going to release the HCl fumes, acidic fumes, if you have an OH attached to this group. You can see the acidic steamy fumes from the HCl gas produced, and you don't even require heating for this purpose. So it's not mentioned over here, but the past papers are definitely going to discuss it. Why? Because in the very next section for PCl3 or PBr3, you can always replace this PCl. That's why we tend to go with PX5 or PX3 as an example to clarify that you can go with fluoro or bromo substitute for these reactions. And in that case, if we halogenate an alcohol, this reaction does require heating. So any PX3s are going to require heating. Any PX5s will not require any heat. Okay. For bromoalkanes or iodoalkanes, we can form PBr3 or PI3 needed for the reaction. Red phosphorus and bromine or iodine are warmed with the alcohol, and that's how we go with these reactions. Now, this specific line, this last line, I clearly cut it down in a different way. Let's underline it. This specific line is telling you that we are forming PBr3 or PI3 in situ for the reaction. Look, he's not directly putting PBr3 or PI3 in the reaction vessel. No, he's putting phosphorus separately, red phosphorus, the formula for which is P4, and he's separately putting either Br2 or I2, and he's warming them along with our alcohol, whatever alcohol is that. Let's consider as an example that it was alcohol, and that's how we go with the reaction. This gives you a clear idea what's happening. And there are more than one examples of in situ formation for these reactions. So if you go with Pi3, heating would give you iodoalkane. which gives us the idea that for TX3s, whether it's PBr3 or PCl3 or PI3, doesn't matter, you always require heat for the reaction to proceed, right? There
Yes.
are other parts of the chapter. So let's stop right here and we'll do the rest of the chapter in the next sitting. We'll start with reaction with sodium metal in the next sitting, right?
All right.